Welcome to part 6 of our series on chemistry, and these will be the chemistry notes. And again, if you've plugged all the way through or pushed all the way through and you've gotten to part 6, I know there's 5 parts and this will be the 6th part. This will be the last. And our chemistry notes are the most extensive notes we will have in any of our units. A lot of the units will be done in 1 part, 2 parts, and even maybe 3 parts, but those parts will be a lot smaller than the chemistry notes. So thank you for bearing with us, and hopefully these notes will help you in class. So today we're going to talk about chemical properties. We're going to talk a little bit about different changes that different compounds or chemical elements will go through. And chemical properties describe the way that an element or a compound reacts chemically with other substances. For example, one of the chemical properties of all the elements in the first family or the first group is that they're reactive with water. And hopefully in class I'll show you a couple of videos of this happening or taking place. Now, that was chemical properties. Physical properties are properties that can be measured and or observed. So you can see what color some of the elements are. You can observe certain properties. These are called physical properties. One example of a physical property is the state of matter. Whether something is a solid, liquid, gas, or plasma, you can observe this. Now the first 3 here, solid, liquids, and gases, you probably are pretty familiar with. Plasma is rare. Now, first of all, plasma, there's a couple different kinds of plasma. There's a state of matter plasma, and you also have plasma in your blood. It's not the same thing. It's got the same name, but it's not the same thing. So when I start talking about plasma, don't start thinking about the plasma that's in your blood. So 3 of those are common here on Earth. Plasma is the one that's not too common here on Earth. The solids, the liquids, and gases all happen here on our planet. Does plasma happen on our planet? Yes, but it's not too often. So you have a solid. What do we know about solids? Molecules are in a fixed position. There's a very short distance between the particles, and there's a great attraction. Now, first of all, these solids, they're still vibrating. These atoms, these elements, they're so small that you can't see them. So it's kind of a weird concept. If you take a look at your hand's actually made up of atoms, and those atoms are vibrating. But those atoms, those molecules, they stay in a fixed position. They don't move. And there's very short distance between the particles, and there's a really strong attraction. That's why solids tend to stick together. That's why when you sit in your chair, it doesn't just move away like air, which is a gas. It's a solid for a reason, because it is solid. But do remember that the atoms in it, the molecules in it, they still are vibrating. They're still moving, but they may be spinning around in a circle, but they're staying put. They're not going all over the place. Now this is different than a liquid. Here there's an intermediate distance between the particles, and there's intermediate attraction. So there's some attraction between liquids, the different molecules, the different particles, but it's only an intermediate. It's strong, but it's not as strong as a solid. A really good example is this. Go to the pool. Do a belly flop. Have you ever done a belly flop? It probably hurts and stings. You might come out and your belly might be all red. But when you hit that liquid, you had that smack. But that liquid did part. It did let you through it. So there's some attraction there that those water molecules did not necessarily want to pull apart. But when you land on it, you force them apart. Now imagine if you tried going to the pool and there was no water in the pool, and you tried doing a belly flop in the bottom of the pool, the concrete. That would hurt a lot more. And one of the reasons why it hurts so much more is because that concrete would not separate. It would not move apart because the bond is too strong. So don't ever do that. I wouldn't recommend it. Where gases, there's great distance between the particles, very little attraction between the particles. And you'll see that all the time. Sometimes you'll come into school, and if you're getting really hungry, I know this happens to me quite a bit, because I'll eat pretty early in the morning. So if I eat at 6 o'clock in the morning, and all of a sudden 10:30, 11, I start to smell some of the food that the kitchen's making. Now, is the kitchen staff, are they bringing the food down to my room so I can smell it? No. That aroma are gases. They spread out from the kitchen. They go in all different directions. Sometimes you'll put a liquid on. Ladies especially, you'll put a perfume on. Sometimes guys, you put on colognes. Now they're a liquid, but they have a very, very low evaporation point. And the evaporation point is low enough so that your body can evaporate the liquid so that it becomes a gas. And that gas spreads out. And that's why sometimes you can smell someone's perfume or cologne here in the classroom. Because there's a great distance between the particles. They want to separate and they want to spread out and occupy every space in this classroom. So if you're a gas, that's the ultimate goal of the gas, to spread out as far as it can go. And if the gas spreads out too far, you actually can't smell it anymore. Not that the aroma's not there, it's just so spread out your senses can't pick it up anymore. So here we see when we go from solids, when we go to liquids, and we go to gases. So you can see right here. Oop, let me get a pen here and make sure I have the right thickness. So when we go from here, you can see how it's all packed together. It's solid. Now these might be spinning, they might be vibrating back and forth. Where liquids, they will occupy the bottom of the container. They will move, they'll be still bonded together, but the attraction is just a little bit weaker. Where gases, they want to spread out in all directions. They want to go in all directions to completely fill the container. So we talked about solids, liquids, and gases. So what about this plasma? What is it? Well, most matter in the universe is actually plasma, just not here on our planet. Anybody know something around us that's plasma, that's out in space that you can see every day? Hint, day. You can see it during the day. The sun, yeah. Stars, and our sun is a star. Stars are made up of plasma. It usually exists at very, very high temperatures, and it requires an electrical charge to occur. Now, this one right here, we can actually see some plasma in this room. We can actually see it in the lighting that we have in this room. Yeah, we have the fluorescent tubes, and in those tubes, there's a gas. And you have, what we do is we create an electrical charge. So right here, we take this electrical charge and we create a gas. Now you might be saying, but Mr. Whittoon, it's not at a high temperature. It's not that hot. Well, they get hot, but it's not that hot. You're right. It's not that hot. You're right. Well, that's because we create a vacuum. And with a vacuum, we can actually change the temperature at which plasma can occur. And you're actually going to see a demo, if you haven't already seen it in class, where we're actually going to boil water at room temperature. And the way we do that is we create a vacuum. And you're going to see that I can actually boil water. Typically water boils at 100 degrees Celsius or 212 degrees Fahrenheit. I'm going to get water to boil at room temperature. Now, we're familiar with these phase changes. When we look at these phase changes, when you go from a liquid to a solid, what do we call that? Well, if you take water and you put it in the freezer, it changes to a solid. We call that freezing. If you take that same ice cube and we put it on the counter, it goes from a solid to a liquid. The ice melted, so we call that melting. If I was to take a little water and put it on the classroom floor, by the end of the hour, it would be gone. Where did it go? It changed from a liquid to a gas. Where did it go? It evaporated, so we call it evaporation. Now, we've heard of this one, condensation. We have gases in the atmosphere, and when they cool off, they change to a liquid. And we call this condensation. If you've ever had a can of soda, and this works really good in the summer on a hot day. If you had a really cold can of soda, you'll notice on the outside of that can of soda, little droplets of water will form. And that's because water condensed. That can was so cold that it dropped the temperature of the air around it, so the liquids, the gas that was in the atmosphere condensed onto the can of soda. And it happens on glasses as well if you have some ice in the glass. Now this one you probably haven't heard a lot about. You can actually go right from a solid to a gas. And a really good example of this is if you have dry ice. Dry ice is actually carbon dioxide in a solid form, and when it melts, you don't want to call it melts, when it changes right from a solid, it goes right to a gas state. Usually, if you do it with water, if you have a solid, it's got to go to a liquid state, then it goes to a gas state. Well, not here. Carbon dioxide goes right from a solid to a gas, and we call that sublimation. And one of the real good examples of this, remember the movie The Wizard of Oz? What happened to the Wicked Witch of the West? Dorothy threw some water on her. What did the Wicked Witch of the West say? She yelled out loud, "I'm melting! I'm melting! I'm melting!" Now, scientifically, that's not correct. The witch was a solid, and she changed right to a gas. The Wicked Witch of the West should have been screaming out, "I'm sublimating! I'm sublimating!" Because scientifically, that would have been correct. So this just goes to prove that movies aren't always scientifically correct. So these phase changes can occur due to a change in temperature, which is what we're used to most often. This is what we see most of the time. But we can actually get the temperature, a phase change to occur with pressure. And that's what I'm going to show you in the classroom. I'm going to take air, I'm going to create a vacuum, and in that vacuum I'm going to have a beaker of water. And I'm going to get that water to boil at room temperature. Not because I'm changing the temperature. I'll prove that I won't change the temperature, but I'm going to change the pressure, and that will cause the phase change to occur. So here's just a little diagram showing how you can go from one state to the next. And it shows the phase changes. This just is kind of an interesting design because it actually, or a picture, because it actually shows you what's happening. If you want to go from a solid to a liquid, what do you have to do? You have to add energy. And remember, solids, these are in a fixed position. They do not want to move, all the water molecules in there. So how do you get them to move? You have to add energy. It's kind of like in the morning. Some of you guys, when you wake up, you're probably not willing to move. So by eating a nice breakfast, you get some energy in you. So that way, by the time you get to science class, you're full of energy and you do well, right? So we're going to talk about two different types of reactions. We're going to talk about an endothermic reaction. And this is a chemical reaction that absorbs energy. Endo is like heating. Endo is like the heat entering. So whenever you see endo, think of entering. It's got those first two letters the same, and a chemical reaction that absorbs energy. So whenever you have an endothermic reaction, energy goes into it. It enters into it. So for example, if you had your solid, say an ice cube, and we want to change it to a liquid, what do? We have to add energy to it. And if we add energy, we get those molecules moving and it will change into a liquid. Now the opposite of an endothermic reaction is an exothermic reaction. Here the energy is being released. So think of it as exiting. So a chemical reaction that releases energy in the form of heat. So what do if we put water? So what happens if we put water in the freezer? What do we want? We want that energy to leave the water. And then it will become a solid piece of ice. So when we have a solid here, if we take and we increase energy, we move to a liquid because we're getting those molecules moving faster and faster and faster. If we continue to add that energy, those molecules are moving faster and faster and faster, and we go to a gas. If we keep adding energy and they move faster and faster and faster and faster, we go to plasma. And the opposite is also true. If we take energy away, we go down this ladder or this stair-step pattern. Here's an interesting thing. If we haven't already done the lab, I'm giving it away, but if you took water and you heat it up, that temperature would rise, 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 rise. Eventually it's going to stop here, and you can't get the water to rise anymore. And that's when it reaches its boiling point. The only way you can get that water to rise even faster is if we captured all that water as it turns to gas. If we capture all that gas and then we heated the gas up, then we could get the temperature to rise. Otherwise, if we do the lab in class, we don't have that. The water will rise. We could start with ice. The water will rise to get to the boiling point, and it will stay put. It will not go any higher unless we capture that gas and we begin to heat up the gas and get the gas to heat up. And the last thing we're going to talk about in our notes is density. Density is a physical property because it can be measured and or observed. So we've talked about that before. And different substances have different densities. And density can be determined by using calculations or comparing them. Calculations is easy. We've done this in the lab. All we do is take mass and we divide it by the volume. And as the volume increases and mass stays constant, the density decreases. Or as mass increases, and if we had volume stay the same, the density increases. So we've done these calculations in class. And we can actually use densities, we can use the differences in densities to identify different substances. So if someone came to me and said, "Hey, Mr. Wattoon, this is gold," I could actually find the density of the object that they gave me, and if the density is what it's listed here, if it's 19.3, then I know it is a good chance that it's gold. But if I check the density of what they gave me and it's nowhere 19.3, it's probably not gold. So if you have any questions with part 6 notes, please give me send me an email or ask me in class, and I'll be happy to sit down and go over these notes with you. Thank you.